Let us discuss the comparison of computational complexity of the direct computation method of DFT versus the FFT algorithms. Here we have listed out the number of points, capital N, complex multiplications in direct computation, which is equal to n square, complex multiplication in FFT algorithms, which is n by 2 times log n to the base 2, and the speed improvement factor, which is the ratio of the two quantities. So in the numerator we have n square divided by n by 2 times log n to the base 2. Now, speed improvement factor for DFTs, we are using only the comparison of the complex multiplications due to the primary reason that multiplication is a more complex operation in comparison to addition. Additions are relatively easy to perform, whereas the more time consuming operations are complex multiplication. That's why we are comparing the two and determining the speed improvement factor. Now for the number of points 4, we get the value here as 16, whereas in FFT it will be only 4. Therefore, 16 by 4 is 4. For value 8 it is 64, whereas here it is 12, so it is 5 times better. For 16 it is 256 and 32, so it is 8 times better. As we move down the list, 128 gives you an improvement factor of 36, 256 gives you a 64, 512 gives you 113, and 1024 points, it is more than 200 times better. So this clearly shows the advantage of using the FFT method in comparison to the direct way of calculating the DFT. Let us now discuss about in-place computation. To understand this, let us consider the basic butterfly structure for decimation in time. In DIT, all the butterflies are identical irrespective of which stage it belongs to. We have two inputs, let's call it as A and B. We are scaling the lower input by produce factor Wn to the power of k. We have -1 to indicate the operation of subtraction, and the final answer, capital A, is the sum of A plus omega n times to the power of k into B, and B is the difference, A minus Wn to the power of k into B. So this is a basic arrangement for decimation in time. What we have to realize here is that the input A and B are complex numbers. So A is a complex value, B is also a complex value. The answer that you get, capital A and B, could also be complex. Now, what we understand is that to store n complex numbers, we need 2n registers. So 2n registers are required to store the inputs. Now what we should realize is that once the input is applied and the result of A and B is obtained, we do not require the inputs anymore. Or, in other words, we can utilize the location which was previously occupied by small a and small b to store the results of that computation. This method of saving is called as in-place computation. That means that the result is updated in the same memory location where the inputs originally were. This method saves the usage of memory locations. Now, from this we understand that the total memory requirement is 2n registers if we are considering the inputs and the outputs. Here's a question from the examination. What is in-place computation? What is the total number of complex additions and multiplications required for n is equal to 512 points if DFT is computed directly and if FFT is used? Also, find the number of stages and its memory requirement. When the question of in-place computation is there, you should draw a basic butterfly pertaining to either DIT or DIF, explain what the inputs are, explain what the output is, and you have to explain about the concept of registers, complex numbers, storage requirement, etc. Okay, so in few lines you should be able to explain what is in-place computation. Coming to the next part, since the problem is for 512 points, we can tabulate the number of complex multiplications and number of complex additions in the case of direct method and the FFT method. Here we have to apply the formula n square. It yields a result 262144, and the number of complex additions is n into n minus 1, which is 26,100. 261632. For the FFT method, the formula is n by 2 log n to the base 2, which is 2304, and complex additions is n times log n to the base 2, which is 4608. Now, to calculate the number of stages of FFT, the formula is log n to the base 2. Answer will be log 512 to the base 2 is 9. The memory requirement which is used here is 2 times of n, which is 2 into 512, 1024. But if we take into account Prudhoe factors also, we are aware that for n point calculation we require n by 2 different Prudhoe factors. If you take that also into consideration, we have to add that n by 2 value, which is equal to 256. So the sum of 1024 plus 256 is equal to 1280. Thank you all.